All right, so what I want to do today is talk about the properties of water. And we're going to start with the chemistry of it and then work our way to the molecule and talk all about water. So water is made up of H2O, 2 hydrogens and an oxygen. Here's the atomic information of oxygen. Here's the atomic information for hydrogen. And I just want to kind of do a review first, and we'll work in groups on this. A lot of this chemistry review is for me as well. But for each one of these atoms, I want you to do the following. Identify the atomic number and the atomic mass. Give the number of protons, neutrons, and electrons in each of these. Draw a Bohr model for each of these atoms with the electron shells and then the electrons and the electron shells. What I also want you to do is find the electronegativity value for each of these using that periodic table. Determine the difference in electronegativity, and based on the number you get, you should be able to tell me what type of chemical bond is going to be formed between oxygen and these 2 hydrogen atoms. And then lastly, I want you to draw a Bohr model for water. All right. So why don't you go ahead and turn into groups, and maybe the first few of these you can talk with right away, and then you can start drawing. Introduce yourselves.
For oxygen and one for hydrogen.
The other one's just one.
Let's start with oxygen. And first of all, what's the atomic number for oxygen?
8.
The atomic number is 8. And what does that 8 represent?
Protons.
The number of protons. And every element on the periodic table has a different amount of protons. That's what makes it unique. They each have their own atomic number. What does this 15.999 represent?
Mass.
The atomic mass. And there's 3 types of subatomic particles: protons, neutrons, and electrons. How much does a proton weigh, an individual proton?
1 atomic mass unit.
1 AMU, atomic mass unit. How much does a neutron weigh?
1.
It weighs 1 as well. What about electrons?
Negligible.
They're super, super small. So they don't even register on the mass scale. So when we're talking about the atomic mass, we're only considering the number of protons and the number of neutrons. So how are we going to figure out the number of neutrons? We know we have 8 protons, and we know that the atomic mass is 16, and that's represented by the number of protons and neutrons. So out of this 16, 8 of those units is represented by the protons, which means the other 8 are represented by what? Neutrons. So there's 8 protons, 8 neutrons, and since this is a neutral atom, it doesn't have a net positive charge. How many electrons is it going to have?
8.
It's going to have 8 as well. 8 protons, 8 electrons, neutral charge. And then what about for hydrogen? How many protons does it have?
1.
It has 1. How many electrons does it have?
1.
It has 1. How many neutrons does it have?
0.
It doesn't have any. The atomic mass is 1, and that 1 is represented by this 1 individual proton. Okay, if there was a neutron there, it would weigh 2. Great, so let's draw a Bohr model for each of these. So here's our oxygen atom, and tell me again how many total electrons we have?
1.
Total electrons in oxygen?
8.
We have 8 electrons. And so we're going to start in the middle, and we put 2 in the middle, which means we have how many left? 6 left. And the way you kind of want to do this, based on the YouTube videos that I've been watching, is you kind of start at the top and you put 1 there, then you distribute them equally across the electron shell. So now we have 1, 2, 3, 4, 5, 6. We need 2 more, and that's when you start pairing them up.
Oh, that makes sense.
So that's our oxygen atom. And hydrogen, just because it has 1 proton, we're just going to get 1 electron up there. 1 proton, 1 electron. And so what's the easiest way for, or how many electrons does oxygen need to become, do they call it stable?
To
To
form
be
an octet.
happy, to form an octet, but why does it want to form an octet? It becomes stable,
Neutral.
kind of thing, I guess. So how many electrons does oxygen need to become stable?
2.
It needs 2. What about hydrogen? It needs 1. Okay. So we're gonna get a chemical bond that forms between 2 hydrogen atoms and 1 oxygen atom. And we want to know what type of chemical bond that's going to form. What are the different types of chemical bonds that we've talked about thus far? Covalent, which is the sharing of electrons, and ionic, which is the taking or giving of an electron. But within the polar, there's 2 types of polar chemical bonds. There's a polar chemical bond, and there's a non-polar chemical bond. And so the chemical bonds that are going to be formed between water, I'll just tell you right now, are going to be a covalent bond. But now I want to know if it's going to be a polar covalent bond or a non-polar covalent bond. And you need to use your electronegativities to figure that out. Okay. Did anybody do that? Did anybody give me the electronegativity of oxygen?
3.5.
What's that?
3.5.
3.5. And what about for hydrogen? 2.1, which gives us a difference of 1.4.
Which is polar.
And so does that make it non-polar or polar?
Polar.
That makes it polar. What's the value it needs to be above to be a polar molecule?
0.5, 0.5.
It's greater or equal to, right?
No.
Yes, yes, 0.5.
Is it equal to or
Yes.
greater than?
It's equal.
It's equal to, yeah.
I thought she changed it to where it was only greater than and not equal to.
That was the
No,
other
she
one.
changed it to that, if
Yeah.
it was 0.5 or higher.
Yeah, if
And
it's,
then the other one
if
is
it's less than 0.5,
then it's
that's
non-polar.
non-polar. And then if it's greater or equal to 0.5, it is, it's polar. And so yeah, this is gonna be a polar molecule. And if the electronegativity value is even higher than that, I don't know what the specific value it is, then what type of bond does it form? At that point, it forms an ionic bond. The electronegativity is just so great that the difference is so great that it just completely steals an electron from another one.
So would it be two hydrogen, so every 4.2?
You mean 2.8?
What?
Oh,
Are you saying, should we consider 2 hydrogens because we're talking about water?
Or are we just doing it separately?
Well, there's gonna be a bond that forms between oxygen and hydrogen. That's 1 chemical bond. And so we wanna know the electronegativity between that chemical bond. Then we're gonna get
Oh.
another chemical bond that forms between the other ones, so we consider them separately.
And so can you tell me why, so they wanna get to 8 and you're doing that based off the valence?
Based on the
electrons?
valence, the
So for
valence
the
shells.
hydrogen, when you say it only needs 1 more, why does it only need 1 more?
Because that inner electron shell only holds 2 electrons. It's stable at 2 electrons.
It's the weird one.
It's
the-
because
It's
it's,
the only one.
It's the only one.
it's because it's small.
So it just
It's so
needs
light.
1.
It needs 2 total.
To be
Or
stable.
will it
Yes,
only
and
need
hydrogen
one?
has
Yeah.
one, and so it needs one more electron to become stable.
But only hydrogen.
Well, only that, yeah, that inner ring is gonna hold two. The
All
rest
the
of
other
them
ones are
hold
going
8
for
until
8.
you get to the larger atoms, and then I think something crazy happens. All right, this is gonna form a polar covalent bond. What does a polar covalent bond look like? Boom, there it is. Here we have our oxygen atoms, our 2 hydrogen atoms, and we're going to form covalent bonds at each of these locations. So we're sharing an electron. And if oxygen needs 2, it can get one of those from hydrogen, this hydrogen, and the other one from the other hydrogen. So when hydrogen shares both of those, then it has a total of 8 in its outer electron shell, and hydrogen has 2 in its inner electron shell. So everything is good. It's a little blurry, isn't it? It's not bad. Oh, I know what the problem is. But what does polarity mean? When you say you have a polar molecule, what does that mean?
Different.
It does, polar opposites. Okay, so they're different. And what this means in the context of chemical bonds is that the 2 ends of the molecule have different electrical charges. Okay. So polarity with regard to a molecule means there's different electric charges on either side of the molecule. And in this case, the oxygen is going to have a partial negative charge, and the hydrogens are going to have partial positive charges. Now I want you to keep in mind that water is a neutral molecule. There's the same amount of protons and electrons in a water molecule. But because of the distributions of the electrons, one part of the molecule is negative and the other part is positive. Why does the oxygen have a partial negative charge?
Lone pairs?
Can you kind of explain?
Lone pairs.
I wasn't thinking of the term lone pairs, but that may get integrated into the equation.
So because it's bigger?
Well, first of all, oxygen has a higher electronegativity.
Yeah.
Electronegativity is the attraction of electrons.
Isn't it like the beehive thing?
Yeah, Jen uses the beehive, the cool house, all that kind of stuff. And hydrogen has a lower electronegativity, and so these shared electrons, because oxygen has a higher electronegativity, are going to spend more time towards the oxygen molecule. And the way I like to think about that, to conceptualize it, is that which one of these has more protons, oxygen or hydrogen?
Oxygen.
Oxygen does. And so protons are positive, so there's a stronger positive force on the oxygen molecule, and so it's pulling those shared electrons toward them, more away from the hydrogen molecule. So there's more positive charge in here, so these electrons, these negative electrons, are being pulled more towards the oxygen nucleus. And so the electrons spend more time there, which gives it a negative charge. All right, are we good on all that? So because water is a polar molecule, that gives it a lot of nice special properties. And these are properties, if water didn't have, we wouldn't be able to survive. So these properties of water are really necessary for life on Earth. And one of the reasons of that is because water is polar, it makes it an excellent solvent. Now, a solvent is a liquid that dissolves something. And the term for the thing that it's dissolving is called a solute. So a solvent, in this case water, dissolves a solute.
Salt.
What were some solutes that you tried to dissolve in lab yesterday in water?
Like vitamin
Salt, sugar,
Vitamin B,
vitamins,
vitamin C,
all
yeah.
that type of stuff. That's the solutes. And if they mix together, if they dissolve, then they form a solution. So water is able to dissolve a wide variety of substances throughout the body, which makes them accessible to the body, to the physiology of the body. It allows substances to flow freely through the blood. The blood is made, the liquid part of blood is plasma. And to be able to travel through the blood, like if you're a glucose molecule, you're traveling through the blood. To travel efficiently, you have to be dissolved in water. If you're not dissolved in water, then you're kind of just rolling along the bottom of the blood vessel, you know, and it's just not an efficient way to go. So what type of substances is water going to dissolve? What type of substances can water dissolve? Well, I'll tell you this. Likes dissolve likes.
Polar.
So whatever properties water has, if the solute has those same properties, then it's going to dissolve. So go to your groups and determine which of these apply to water. Polar, nonpolar, hydrophobic, hydrophilic, lipophobic, lipophilic. Talk with your group about this real quick.
It's like stay away from
Yeah, that one was the electron.
5.
Okay. And so it's polar. Yeah.
So
All right, let's go through these. So which of the following apply to water? Well, the first one we've already established. Is water polar or nonpolar?
polar.
Polar, good. Hydrophobic or hydrophilic? First of all, what does hydro mean?
Water.
Hydro means water. What does phobic mean?
Get away from it.
A fear of. What does philic mean?
A love of furniture.
A love of, okay? So this is water going to be hydrophobic or hydrophilic?
Hydrophilic.
Hydrophilic. It loves water. It is a water molecule.
It loves itself a lot. That's why it holds it so good. So good.
And what is lipo referring to?
Fats.
Fats, lipids. So is water going to be lipophobic or lipophilic?
Lipophobic.
Water is lipophobic.
Lipophobic.
Oil and water do not mix. So water is lipid fearing. And
And
in this picture, here's all the water, and you know, it's just trying to get away from the oil. It doesn't want anything to do with the oil. So it's lipophobic.
Hydrophilic.
So any molecule that is polar, hydrophilic, or lipophobic can generally be dissolved by water. And generally, if something is polar, that means it's also hydrophilic and lipophobic. If something is hydrophilic, that means it's lipophobic and polar. So all of these things go together.
So, okay, so the polar, if it's polar, it will also be hydrophilic and lipophobic.
Yes,
Okay.
yes. Okay. All right, so here's your next assignment. And some of you may have done this in lab the other day. I want to know which of the following dissolve in water and why, if you can. So the first one, you're going to work in groups on this. First one is glucose. Here's a glucose molecule. This is a carbon ring. Okay, if it's not shown there, the atom's not shown, that means it's carbon. Carbon is the basis of living organisms. So this is glucose. Sodium chloride. This group of vitamins right here, the B vitamins, of which there are like 7 or 8, and also vitamin C. Okay, these are classified as a certain type of vitamin. So I want to know about these vitamins. Do they dissolve in water? What about these vitamins here? A, D, E, and K. Okay. Then I want to move on to some different types of hormones. And you may have to do a little Google searching to determine if what properties these have. But 2 of the hormones I want you guys to consider are estrogen and testosterone. Anybody know what classification of hormones these are, estrogen and testosterone? These are steroid hormones. These are steroids. Where's estrogen produced?
Ovaries.
The ovaries. Where's testosterone produced?
Testicles.
The testicles.
And A little bit in the adrenal gland.
and a little bit in the adrenal gland. So there's really only two places in the body that produce steroid hormones, the gonads and also the adrenal glands. But the adrenal glands are producing like cortisol, aldosterone, stuff like that. So, you know, estrogen and testosterone are released into the blood. Do they dissolve in water on their own? It's a good question. Here's another hormone. This is insulin. And insulin is not a steroid. Insulin is a protein hormone. So it's a protein. It's made out of these individual amino acids, and then it bends back on itself because of intermolecular forces, and it forms a 3D shape. Is insulin going to dissolve in water? Do I have any more? No, those are them. So go through there and tell me if each of those dissolves in water, and you know, if you can, why.
No salt.
So, glucose and sodium chloride are solvents. The first class of vitamins he showed, are called water soluble. Soluble.
Yeah.
Those are fast soluble.
Well, you should get exposed to these, you know, at some point during these series of classes you take. All right, let's go through these here. Here we have a glucose molecule. Is glucose polar or non-polar?
Polar.
It's polar. Okay, it's going to dissolve in water. I'll show you some pictures here in a second, but I want to go through these first. Sodium chloride. And first of all, can anybody look up real quick the electronegativity difference between sodium and chloride? What's the difference in electronegativity?
It's
0.
Oh, I was looking at it wrong.
2.1.
Yeah.
That's the difference, right?
Yeah.
Is that a large electronegativity difference?
Yes.
It's super large. Which one of these, which sodium or chloride, which one of those has a higher electronegativity?
Chloride.
Chloride does. So it is just tugging on that extra electron from sodium, and it tugs so hard that it actually steals it,
So it's an ionic bond.
which is an ionic bond. Okay? And because it completely stole this electron, that's why the chloride portion of sodium chloride has a negative charge, and that's why the sodium has a positive. But there's a little there's a little bond between there. I guess it's an electromagnetic attraction where opposites attract kind of thing.
Yeah.
That's what's making this ionic bond.
How do you know, is there like a way to know based on like
Numbers,
the
electronegativity
ions or
numbers.
something to know whether it's going to be covalent or ionic?
Yes, there's a number for it. If it's, I don't know what the exact number is, but once the electronegativity gets above, I don't know, like 1.7 or something like that, then that difference is large enough where it's going to completely steal an electron. So is sodium chloride going to dissolve in water?
Yes.
How come? It's polar. This side of the molecule has a negative charge, this side has a positive charge. What do all these vitamins have in common, the B vitamins and vitamin C? What do we call this classification of vitamins?
Soluble vitamins.
These are water-soluble vitamins. So just by that term, are they going to dissolve in water?
Yeah.
They are. What about vitamins A, D, E, and K? That's
Fat
what I
soluble.
remember.
Fat
They're fat soluble. Does that make them lipophilic or lipophobic?
Lipophilic.
They're lipophilic. Do lipophilic molecules dissolve in water? They don't. Fats and waters don't mix. What about estrogen and testosterone? What did you guys come up with?
They're lipophilic.
Non-polar.
They're both non-polar, or I think a better way to remember them is they're both lipophilic. All steroid hormones are derived from cholesterol.
So those are.
Estrogen, testosterone, cortisol, aldosterone. All of those at one time were cholesterol, and then different enzymes convert them to different steroid hormones. And cholesterol is a fat. So that makes these lipophilic. And if they're lipophilic, then they're hydrophobic. They don't like water. So they're not going to dissolve in water on their own.
So then what about like insulin that you would inject to yourself?
Well, let's go to
Is it the
insulin.
same?
What did you guys come up with insulin? Is it going to dissolve in water on its own? Why don't you, well, everybody first, is insulin going to dissolve in water on its own?
Yeah.
I get some no's. How come you guys are saying that?
What part of
The
it?
internet told me
What did the internet tell you?
it was non-polar, right? Is that what it told us?
Well, that's what it said when we first
Let's get some clarification here, because this was another internet search that I put
Yeah,
in more faith.
so, the outside is, is mainly polar, the inside is mainly non-polar. Yeah, it's so.
That's good enough for now. The insulin molecule, it's a 3D protein, and the inside of it is non-polar, and the outside of it is polar. And that's why it's arranged the way it did. Okay, the polar molecules want to be on the outside interacting with water. So the outside of insulin is polar, which means it is going to dissolve. So let's just go through some pictures here. First of all, here's glucose. And you can see that glucose is being surrounded, it's being dissolved by water. Now, these are not chemical bonds that are forming between water and the glucose molecule. This is a type of intermolecular force. And what type of intermolecular force is going on between the water molecule and the glucose molecule?
Hydrogen bond.
They look like hydrogen bonds to me. Here we have a positively charged hydrogen molecule. Whenever a positively charged hydrogen molecule interacts with any negative molecule, that's a hydrogen bond. So in this case, the positive hydrogen from the glucose is interacting with the negative oxygen from water. That's a hydrogen bond. And you can see it surrounds it. It surrounds the glucose molecule. All right, the fat-soluble vitamins, what did we say about those? Are those going to dissolve? They're not. And whenever something won't dissolve in the blood, in the water, the body has a solution for that. Because we want everything in the blood to be dissolved for the most part. Anything we want to transport through the blood, we want it to be dissolved in water. So if it's not going to do it on its own, the liver produces what we call these carrier proteins. A lot of these are called albumins. So the liver produces these carrier proteins, releases them into the blood. These carrier proteins bind to whatever they were made to bind to, in this case, these fat-soluble vitamins, and that carrier protein makes it soluble in water. The carrier protein itself is soluble, so it binds the vitamin and it solubilizes the vitamin by doing that. So you get these carrier proteins. What about these water-soluble vitamins? Well, yeah, they're going to dissolve on their own. Emergency, you just take these little packets, put it in water, it dissolves. Vitamin water actually does have some vitamins in it, and I was trying to get trying to find a good label that had the nutritional values and stuff, but it was all blurry. So this just says we added B vitamins. So there are B vitamins in there, and they're solubilized in water.
Vitamins plus
So
water.
the carrier proteins,
Let's take a look at
are
another.
they non-polar? Does that make
The
sense?
carrier proteins are polar
Oh, wait.
because they're gonna surround themselves in water.
Maybe the opposites, right?
Wait.
What's that?
If they're not water soluble, then it attracts some like a polar. So like opposites attract.
You mean the carrier protein
Yeah.
versus? No, that's more of like a lock and key kind of thing. It's not a chemical bond. It's an
Okay.
actual It's an actual, like a 3D protein binding this,
So
whatever it
would
is.
it be similar to how insulin works, where it has a part that is?
We're getting to
older-
insulin.
Yeah. No.
Anybody else? Okay, what did we say about insulin? Insulin, the outside is polar, it's gonna be dissolved in water. And what this is an insulin molecule, and it got released from the blood, and here's a cell. This is a cell, and insulin is gonna act on this cell. But what I want you to notice is that there's not a binding protein around insulin. Okay, it dissolves on its own. This, on the other hand, testosterone is lipophilic. It's not going to dissolve in water. So testosterone, estrogen, and all the other steroid hormones require a carrier protein. And the carrier protein takes the hormone to the cell, and then it drops it off. Now, we're going to get to this later, but the slide is up here, so I might as well talk about it. Testosterone is lipophilic, right? It likes fats. This is the plasma membrane of the cell. That's made up of phospholipids. So things that are lipophilic can diffuse right through the plasma membrane. And that's what it's showing testosterone doing. It drops it off at the cell. Testosterone just diffuses right on through into the cell. And then it binds to its receptor inside the cell. Insulin is lipophobic. So it cannot diffuse through the plasma membrane on its own. And so what it does is it binds to what we call an insulin receptor that's located on the plasma membrane. And that activates the cell.
A receptor, what is it?
This is a hormone receptor,
Ah.
and specifically this is an insulin receptor. And it's located on the plasma membrane because insulin is lipophobic and it can't diffuse into the cell.
And so that's what the insulin receptors are for, to help it.
It activates the response by binding to the receptor. It binds to the receptor, it activates what's called this signal transduction pathway within the cell, and then you get whatever desired cellular effect you have. What happens when insulin binds to a cell? Why does it do that? What does it allow the cell to do?
It allows
First of all, where is insulin produced?
in the pancreas.
In the pancreas. When is insulin released by the pancreas into the blood?
In response to more sugar.
When blood sugar is high or is low?
High.
It's when it's high, like after a meal. And you have all these sugar molecules going into the blood, and your blood sugar goes up to, I don't know, like 180. That means you're hyperglycemic, you're above whatever the normal level is. And when that's the case, insulin is released by the pancreas detects that high blood sugar, releases insulin, insulin binds to its receptor, activates the cell, and what it does is it opens these glucose transporters, and it actually allows glucose to move through these transporters, through these channels, into the cell. Actually, it's a transporter. And so by taking it out of the blood and moving it into the cell, you're bringing blood sugar back down.
So it releases the insulin, it binds it to the receptor.
Yeah, you know, and
then-
this is just
Okay.
kind of extracurricular activity. I'm just kind of going off on a tangent. Eventually, we'll cover this, you know. Okay. All right, let's take a break. Let's just take maybe 5 minutes or so, and we'll come back and we'll finish what we're gonna do. All right, let's carry on and finish here. Lastly, let's talk about how water is going to solubilize sodium chloride. First of all, did you guys do sodium chloride, which is table salt?
Yeah.
Did you guys try to dissolve that in lab yesterday? Did it dissolve? Easy. Okay. Easy peasy. And why is that the case? Well, both water and sodium chloride are both polar. But I want to take a little closer look at how these are going to interact, like what's going to be involved with the dissolving process. So you imagine you put sodium chloride and expose it to water. How is it that, well, I guess we haven't talked about this part yet, but the sodium chloride itself is not fully dissolved in water. What happens to this sodium chloride molecule?
It breaks it.
It actually breaks, all right? And so the water is dissolving individual sodium and individual chloride. It's not dissolving the molecule itself. So how does that happen? You put sodium chloride in water, and what part of that water molecule is going to be attracted to the sodium ion? So these guys, you put it in water, and the molecules are going to orient themselves based on all these chemistry that we've been talking about. What part of the oxygen molecule is going to be touching, is going to orient itself with the sodium?
The lone pairs.
The oxygen or the hydrogen atom?
The oxygen.
The oxygen. And why is the oxygen part going to orient towards the sodium?
Because it's
Opposites attract.
Because it's gonna have.
Negative partial charge of the oxygen, positive partial charge of the sodium. And what part is going to orient with the negatively charged chloride?
Hydrogen.
The positive hydrogen. And those ionic bonds, are those generally strong or weak? Those are kind of some of the weaker chemical bonds. And so these water molecules are going to surround sodium and chloride, and they're actually going to pull them apart. What does that look like? And I was going to have you guys draw this, but I'll just go ahead and show you a picture. Here's a sodium chloride crystal with these partial charges. You put it in water, and here's that positively charged sodium just being surrounded by all the partial negative oxygens. Okay, it dissolves that. And here's the negatively charged chloride being surrounded by the partial positive hydrogens. And so each of those atoms is dissolved individually. Why is solubilized sodium important for the body? Why can't, can the body use sodium chloride on its own? It can't. It has to use the individual atoms, the individual ions. And this is just an example I'm going to come back to on the importance of sodium. Sodium is critical for nervous system function. If your sodium imbalance is off, you're going to have problems with your nervous system. And the reason it's important is because sodium running down the neuron, this is a neuron here, generates electricity. The nervous system communicates with electricity, and the flow of sodium through these neurons is electricity. And something that we'll talk about in AMP, but it's great to introduce it right now, is that on the inside of the neuron, at rest, there's a negative charge. It's like minus 90 millivolts. And it takes energy for the neuron to create that negative charge, but it's there for a reason. And that's because what happens is whenever these gated channels open, sodium floods into the cell. Based on Susanna's video that you watched a couple weeks ago or last week, does sodium have a higher concentration inside the cell, outside the cell, or inside the cell? Is the concentration of sodium higher outside the cell or inside the cell?
Outside.
Outside the cell. And so because of that, when these channels open, sodium rushes down its concentration gradient inside the neuron. And once it's in there, what does it do? It follows this negative charge. And so now you have sodium flowing down the neuron. And the flow of sodium in the body is what electricity is in the body. So you get this electrical charge that's going down there, then it hits the end of the neuron, and that's where it can interact with a muscle and stimulate it. It can interact with another neuron, release neurotransmitters, all that type of stuff. All right, let's move on. Water is an excellent solvent. That was the whole point of that, based on its polarity. The next thing I want to talk about, an important property, is that water molecules are bonded to other water molecules by weak chemical bonds that we call, what type of bond is this with a positive hydrogen? to another negative there. That's a hydrogen bond. That's an intermolecular force. That's a hydrogen bond.
Why do you call it a weak chemical bond? I thought that one was the strongest.
No, it's one of the stronger ones out of the intermolecular forces, I think.
Oh.
Out of the, so chemical bonds are stronger than intermolecular forces.
Oh, so like covalent and ionic are chemical bonds.
Covalent, ionic, those are stronger than the intermolecular forces.
Gotcha.
Okay. And the intermolecular force that's attracting these water molecules together is a hydrogen bond, where you have a positively charged hydrogen having this electrostatic attraction to the negative oxygen.
And that's when you're talking about the electronegativity between them? Is that what you mean?
Well, electronegativity is used to form chemical bonds. This is an opposites attract type of thing, but it's an attraction, it's not a chemical bond. And you know, hydrogen bonds not only form between water molecules, but anywhere on these larger molecules where you have a positive hydrogen and it's interacting with this negative oxygen or a negative, what are some other examples that Jen used the other day? Oxygen,
Oh,
I think
yeah.
nitrogen, maybe
So it's like
fluorine,
hydrogen.
yeah, something like that.
Yeah, what was it? I can't remember.
So this is what water looks like. You have these individual water molecules and they're forming and breaking, they're constantly forming and breaking these hydrogen bonds between them. And individually these hydrogen bonds are weak, but you have enough of them and it creates a little bit of a force. And so it's these hydrogen bonds that produce the phenomenon that we call cohesion. Cohesion is the attracting of water molecules to each other, or of molecules to each other.
So that's why the paperclip floated on water and not hexing.
We're not quite there. That's related to it. But what did you do in lab the other day that demonstrated cohesion?
The penny drop.
Water drops on a penny. Okay, they covered it and then they formed this dome, you know, because they're held together by those hydrogen bonds.
Or is it like her walking in pants through the wet field example?
Yeah, that's an example of, so water gets down there and
The water grabs to itself.
Well, it depends how high the field was, because
that's actually osmosis, I guess. It's water moving from an area of lower to higher concentration, higher to lower concentration.
Okay.
Yeah. So anyways, the phenomenon of molecules attracting each other is called cohesion, and cohesion produces surface tension. Surface tension is a measure of the attraction at the surface of a liquid. And so the reason these water skiers can be on top is because their legs, they're bending the water there, that's kind of cool to look at, but they're not breaking those hydrogen bonds.
Yeah.
Okay. And these properties are alive and well inside the body. And this is an example that I want to look at to demonstrate that. This is in the lungs. So just to kind of get you into the respiratory system, if you run your finger up and down your neck on the anterior side of your neck, you can feel these little plates running horizontally across. Did you guys feel those?
Mm-hmm.
Those are cartilage rings that wrap around your trachea or your windpipe. So your trachea goes down your neck into the thoracic cavity, and about mid-thorax region here, it branches. One branch goes into the right lung, the other branch goes into the left lung. And those are called the bronchi, the right and the left bronchi. Once it gets within the lungs, those bronchi branch and branch and branch, like 23 times. And that forms what we call the respiratory tree in each lung. But at the very end of those branches, at the very end of the respiratory tree, you get to these little air sacs that are blind at the end. It means there's no way out. And does anybody know what these little air sacs are called?
Alveoli.
Those are alveoli. Singular is alveolus, plural is alveoli. And these are little air sacs where gas exchange is going to occur. And the lungs is made up of millions and millions of alveoli. If you look at histology or a microscope slide of the lungs, you just see for the most part these alveoli. Every once in a while you'll see a big branch in there, but most of it's made up of these alveoli. And wrapped around the alveoli are blood vessels that we call capillaries. So for blood vessels, you have arteries, veins, and then you have capillaries. And capillaries are the smallest, and this is where the exchange of materials occurs. So this is the interface that we're going to exchange gases from the lungs into the blood, and from the blood into the lungs. Just because we're here, well, let's look at this picture now. This is a close-up of that. This is one individual alveolus. And this is a capillary that's wrapped around it. And they're stuck together in what we call, this is called a respiratory membrane. So it's where the air sac of the lung binds together with the capillary. It's a real thin membrane, and this is the membrane that gases are going to be exchanged across. What gas do we want to move from the lungs into the blood?
Oxygen.
Oxygen. And that's what's being shown right here. What gas do we want to move from the blood into the lungs so we can exhale it?
CO2.
Carbon dioxide, and that's what we're showing right here. This is where it gets a little interesting. If you notice on the inside of this alveolus, there's a thin layer of water. And all of these alveoli have a thin layer of water inside of it. And the reason that's there is because it's required for efficient gas exchange of oxygen. If that wasn't there, you wouldn't get very much oxygen moving into the blood. And just to visualize that, if you didn't have this water there, the oxygen would be bouncing off the alveoli, and eventually some would make it through here. But I think what this water molecule does, or this layer of water, is it traps the oxygen in there. And once it traps it in there, then it's just bouncing off, bing, 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 bing. It's making a lot more contact with the alveoli. And so it has a better chance of diffusing into the blood. So that's why it's there. The layer of water is there for the efficient exchange of gases. But can anybody think of a problem that would create? And think about this. When you inhale, your lungs and all of your individual alveoli are expanding. Why would this layer of water create a problem when you're trying to inhale and expand those alveoli? And it has to do with cohesion.
Yeah.
These water molecules all have hydrogen bonds. There's cohesion within those water molecules. What that means is that if there wasn't a solution to this, and there is, but if there wasn't, what that would mean is that every time you inhale, in order to expand these alveoli, you'd have to break those individual hydrogen bonds, break that cohesion. And that takes energy to do that. Okay. So what we want is a molecule in there that's going to break those hydrogen bonds on its own. So we don't have to do it by force, by skeletal muscles when we inhale.
And that's where the oxygen comes in? Or
Does anybody know what molecule is going to be released into that thin layer of water that's going to break hydrogen bonds and therefore get rid of the cohesion between the water molecules? You may have heard it in a medical context. Surfactant. You're like, no. So this is what surfactant does. This is an alveoli, and this is what we call an alveolar type 2 cell, and it's producing these surfactant molecules. And surfactant is a phospholipid molecule. It acts like a soap. This is it right here. You have a phosphate head and then a fatty acid tail. And this phosphate head is hydrophilic. And then the tail is hydrophobic. But anyways, this cell releases surfactant in there, and what the phosphate head does is it gets in between those water molecules and it breaks those hydrogen bonds. And so it's getting rid of those cohesive properties. Has anybody worked or had any exposure to premature infants, premature babies?
Well,
I was
in-
one.
Uh-huh.
Yeah.
Okay.
Yeah, like Friends as babies or like just movies.
Yeah, so one of the things that you have to be concerned about with a premature baby is that all of their organs aren't necessarily developed where they're supposed to be. A premature baby can come out with jaundice, a yellowish cast to the face because their liver's not developed properly. Another thing that can happen is their lungs aren't fully developed and they don't have a lot of these cells that produce surfactant. And what they call that, when a premature infant lacks surfactant, they call that infant respiratory distress syndrome. And why is that such a problem for this little baby?
They can't.
Because
They
they can't breathe, get enough oxygen.
It takes a lot of work for them to expand their lungs and to breathe.
And
They
they're
don't
already
have
weak.
a lot of.
And they're weak to begin with. Yep. And so that can be really hard. But they do have what's something that you, what are they doing in this picture to solve that problem?
Air pressure to open a lung.
They're breathing.
No, because that would take, to constantly, that's like a ventilator, and we're not necessarily putting it on a ventilator. There's surfactant in this bottle. And they're actually putting that surfactant down the trachea, and so it'll eventually get down into the alveoli.
So basically, they're like rebuilding it or something, or?
Well, they're producing surfactant because the body isn't.
Right.
And then eventually, as the baby develops, it'll be able to
It will
produce it on its
produce it
own.
on its own.